Yeah, I'm sitting here in the School of Geosciences up in the University of Aberdeen. So, geoscientist, I'm going to assume that not everybody on the call knows very much about sedimentology. So, I'm going to take you on a little bit of a journey through sedimentology. There's going to be some graphs, but hopefully we can get through them. They're not going to be too scary, and I'll talk you through them all. We're going to step away from Scotland today, and I'm going to take you to what was originally my PhD study area many years ago, the Gulf of Cadiz, just the south of Spain and Portugal. And we're going to talk about the microplastic distribution there in the deep sea. So we're talking about over 300 meters water depth on the shelf and into the abyssal plain. A couple of quotes just to get started, just to show you why it's relevant that we might want to have a look at these microplastics. And some of the quotes that I've taken out of the literature, they're really hard hitting. So first point to make you aware of is that plastics, when they enter into the environment, they never decay or dissolve. What basically happens is that they just get broken up into smaller and smaller pieces, and eventually into very, very tiny pieces, sub-millimeter scale, and those become microplastics. So they hang around for a very long time. They're a true anthropogenic sediment. And we can think of them as a sediment once they get to microplastic scale. They move around just like sand. So they're present for a very, very, very long time in some form or another. And the graph there just shows the cumulative production of plastics over time. So you can see that we are absolutely so dependent on these in our modern lives. We use them in all sorts of things, medical, packaging, food, etc. So they're plentiful and they're going to stay around for a very long time. The second quote I want to take you to is, and this always shocks me, is that so we know an awful lot about where plastics are sourced from. We know where they enter the environment, and then once they get into the ocean, we know that there are vast areas. You might have heard about the Pacific garbage patch, vast areas in the ocean and in our waterways where they accumulate in these surface waste patches. And I've shown an example of a photograph here of what these might look like. But actually, it's estimated that 99% of our global plastic budget, that's the plastic that we know comes from sources around the world, is unaccounted for in these surface waste patches. And that sort of leaves a very large question to answer, is where do these plastics go to? Where are they ending up? And the answer is going to be in the deep ocean at some point. They're going to sink and end up on the ocean floor. So we see the ocean basins as kind of an ultimate sink for microplastics. And this is a fantastic paper. I would recommend, if you're interested in this, to go and read this really good summary paper by Kane and Claire back in 2019 that sort of starts to ask a lot of research questions about where these plastics go to in the deep marine. The deep ocean, I'm sure many of you are aware, is highly complicated. It's not just a basin, it's a really dynamic area. We've got a lot of sediment processes acting in there, lots of ocean currents, lots of gravity processes settling through the water column. So it's a really dynamic space. So when we got microplastics or plastics in general entering the ocean basins, what happens to them? Is there areas where they're going to be preferentially deposited and buried, so sort of sequestered into the subsurface? And is there places that we're less likely to find these deposited? And that was one of the drivers for this research. So the objectives, I'm sure many of you are aware, and when you're working in anything offshore, it's very, very expensive and very difficult to source data, fresh data. So this was a small pilot study that I'm going to talk about today, where I looked at some legacy core from the Gulf of Cadiz that had been collected many years ago to see if we can use that legacy data to understand microplastic distribution in deep marine settings where it's too expensive for me to go out and collect in a small pilot study. And then look at some of the controls on this microplastic distribution. Is it just a simple case of we get more microplastics close to the source, so land, or is there some sort of overprint of a depositional process? So I'm going to take you through that. First, the data. So as I mentioned before, this was my PhD study area, the Gulf of Cadiz. So I went out a few years ago now, I'm not going to say how many, and collected some of this data myself, which was, well, with a larger team, of course, which was a fantastic opportunity. And actually, at the time, one of our piston cores did capture an entire plastic bag, and it ended up ruining our seabed sampling at that location. So we knew that there was plastics about. And when I was doing my sedimentology analysis, I could see them under the microscope. They were around. But at that time, it wasn't the focus of the study. Didn't really think much more about it until more recently when I was like, oh, maybe I could go back and have a look at these microplastics that we saw originally. And I went back and used my own PhD sediments, but then also a number of other sediments from cores that were gravity cores that were collected up to about 30 years ago. So the Gulf of Cadiz and the margin around Iberia is a fantastic area to collect data because it is controlled. All the deposition is controlled by what's shown in pink here, which is the Mediterranean outflow water. Sorry, I've lost my camera. So that Mediterranean outflow water, it's water from the Mediterranean. It's accelerated through the Strait of Gibraltar and enters into the Atlantic Ocean. It can get very, very high velocities, in the order of a meter or a couple of meters per second. So it's a very vigorous water current. And that interacts with the seabed and it generates these sediments that we call contourites. And this is an example from a seismic section. So these ocean currents can erode. So here we've got what we call moat, but an erosive channel. And then in other places, it deposits large sediment drifts. So these ocean currents kind of control the deposition, but there's a lot of other things going on in the area. And really, all ocean sedimentology is controlled um, by these end members of bottom currents that create contourites, gravity-driven currents that generate turbidites or mass wasting deposits, and pelagic settling, so sediments and probably microplastics floating down through the water column and accumulating in the deep ocean. So this map kind of shows a summary of the results in general, and I'll guide you through this a little bit. So the size of the bubbles here indicates how the relative amount of microplastics per gram that we found in the seabed sample. And then they're colored based on mean grain size. So mud from finest up to fine sand is about the coarsest grains that we get. And really interestingly, there was no evidence of any correlation between water depth and microplastic concentration. I've added on the influx coming from rivers there, and you could maybe make a story around that, but there's no clear link between the source and the number of microplastics that we're seeing. And that's shown on this graph on the right-hand side. I've highlighted in orange some clear outliers, and actually when we were sampling in some of the cores, you could visibly see contamination. So this is definitely an issue of using older cores where there's no contamination mitigation that has been going on in the last, when it's been stored or when it's collected. So I've excluded those from the study. But we've still got a considerable number of samples there that I wanted to test to see if we could see any trends in the data. And really astonishingly, despite some of these cores being like 30 years old, there is really clear trends in the data. And so this graph on the right-hand side shows microplastics per gram on the vertical axis and then mean grain size on the horizontal axis. And you can see that in the very fine grains, in your muds and fine silts, there's a clear trend of increasing microplastics per gram. And then once you get into the coarser sediments, into your medium to coarse silts and fine sands, there's a sudden drop in the microplastic concentration. And that sort of indicates that there's probably a depositional control going on here. So I wanted to investigate that a little bit further. For those that aren't aware of these grain size trends, a little bit about what we do. So we basically take our sediment or soil sample and we run it through a laser particle analyzer. And this is our one here in Aberdeen, and it spits out a grain size distribution curve. So it shows the relative weighting of different grain sizes and their concentration, basically. And there's a whole suite of things that you can do with these grain size distribution curves, lots of statistics that we can get out, including here simply the cumulative frequency curve of this histogram. But we can do all sorts of other things like understand grain shape, size, and do lots of cool statistics on them. And I'll run through these statistics very quickly, just going to touch on two. So sorting, so that is the standard deviation of our grain size distribution. Basically, how well sorted is the sediment? Everything here is very poorly sorted. We've got wide grain size distributions, and you could say that the poorer the sorting, the more likely there's likely to be more microplastics per gram. The other statistic I'm going to focus on is skewness, and that is, the skew away from a normal distribution. Everything has a coarse skew here. And again, the more skewed it is, the sort of less likely you are to have a high microplastic concentration. These aren't particularly helpful in their own right, but when you cross plot sorting and skewness, so skewness on the vertical axis, sorting on the horizontal, there's some really interesting clusters start to develop, and I've labeled them A to G. So I started thinking, well, what's causing these clusters? And when I plotted the grain size distribution of those, you can see that these really do all look very different, these grain size distributions. And you can start to assign depositional environments or depositional processes to them. So cluster A is a really stereotypical pelagic sediment where all the sediment's been settling through the water column. We've got a pretty normal distribution, lots of peaks that correlate to probably different sources of sediment. Very typical pelagic sediment. And then as you move towards the right, these are getting to very stereotypical contourite, so ocean current influenced deposits. So that's telling us something about the depositional processes. This here is the cumulative frequency curve. So it's the same data as this. It's just plotted as a cumulative graph, basically. And from this, we can sort of make assumptions on the depositional processes that generate these sediments. In the finer grained, you can see that there's a number of breaks in the slopes. So in the finer grained, we're attributing this to suspended load. So sediment grains that are moving through the column. And then when we get down to the coarser grain, these are different components of the bed load, so rolling or jumping along the base of the flow. How does this relate to the microplastics is the main conclusion we want to make here. So now I've taken that same cross plot and I've made the bubbles, the data points bigger or larger depending on the microplastic concentration. And you can see that we've got more microplastics in clusters B, C, and D. And these three clusters are those that are dominated by suspended load. So we get low microplastics in pelagic sediments, and then in very fine grained contourites where we've got low ocean current velocities, we get a high concentration of microplastics. And this is all pointing towards there being a really strong depositional control on where microplastics are likely to be deposited and accumulate. And therefore, these are areas, these contourite sediments are potentially areas where we might get microplastics accumulating and then being buried into the subsurface, into the geological record. This is definitely an area for more investigation. There were definitely issues with this data set because we were using such old sediment cores, so contamination is a real problem. But I think that there is enough evidence here that there is some relationship here that we can extract from the sediments. There's not simply a clear-cut relationship between distance from source and where microplastics are deposited. There's something else going on. And this is sort of tying into future work. So my next step was I would really like to get some funding to go out and sample these. And I guess a call to action for you if you're working offshore looking at microplastics and you want to get a sedimentologist involved, let me know because I would love to get some samples that we have a stronger control on the contamination issues. But the current work they're doing, we're just out offshore Aberdeen here over the summer looking at basically the source to sink story. So I've got Judith's name there in the bottom there. She's researching here in Aberdeen looking at a river catchment distribution of microplastics. And then we're sort of taking that to the next step of understanding how we get from the river mouth into the deep ocean. So yeah, lots of unanswered questions here, and I'm really looking forward to seeing what kind of questions we get. But do let me know if you're interested in sort of taking this sort of work forward and looking to collaborate. Thank you very much.
So, hello everyone, and thank you for being here. And excuse my voice today. It's perfect time as usual. I have a cold coming up. So today I'm gonna be talking about this new upcoming industry, and even though it's new, or relatively new, we've been aware of the environmental problems and challenges for quite some time now. And strictly speaking, this has never been like my official research topic, and I came to it a bit indirectly. So as Dominique said, I'm a deep sea ecologist, and currently I'm a postdoc at the Lyell Center, Iowa University, but not for much longer. So before we start with all the nitty-gritty details, here's my background. I originally come from the northwest of Italy, as you might know by the accent, and I come from a white region, and that is called Colli Tortonesi. So here people in Scotland had breakfast, and I had better wine growing up. So I moved to Scotland to start my degree in marine science at SAMS, and then moved to Edinburgh, Iowa University, where I did my PhD and postdoc. For both of them, I was looking at the impacts of deep sea mining in the Clarion-Clipperton zone. And then for my PhD, I also looked at the impacts of climate change in fjords along the West Antarctic Peninsula. And when I was finishing my PhD, a startup called Syncolab, who was developing a carbon sequestration technology, I signed a lot of NDAs. So if you're really interested in this technology, I'm afraid I cannot say much. Asked for my expertise regarding the bent ecosystems. And here's where I started getting interested and on this upcoming industry. And as I was learning about it, I kept thinking, as if the ocean don't have enough to worry about it. Here we are stating that we are going to solve the impacts of climate change by going to modify the marine environment even more. But I'm sure you all know about this. So climate change. I'm sure I don't have to explain this climate change to this crowd. And spoiler alert, it's happening. And if you don't think so, please, this is not your kind of talk. We all know how important it is to find a solution to this problem and how urgent this need is. So, considering that the ocean has absorbed about 90% of the excess heat since the industrial age, now the consensus is to harness the power of the ocean to restore the climate. What a sales pitch. So how can we say no to this? So the different ocean-based carbon dioxide removal technologies are many, various, and expand from coastal water to the deep sea. And this includes electrochemical ocean carbon dioxide removal, restoring living blue carbon, microalgae cultivation, macroalgae, deep sea storage, for example, carbon capture and storage, in the form of liquid CO2. We have ocean alkalinity enhancement and artificial upwelling and downwelling. To consider that some of these approaches are still at the theoretical stage and have never been tested, and thus the overall CO2 removal potential remains uncertain. To be honest, most of these remains uncertain, as most of them is not really done in large scales, but just pilot studies. But anyway, so For time's sake, I'll be focusing on the following today. So it's ocean alkalinity enhancement and macroalgae, and then we're going to look at the challenges and future perspectives. So these two, I also focus on these two because right now within Europe and the US, these are the main two like research topic. If you leave out like carbon capture and storage, like as liquid CO2, and blue carbon has been like quite a hot topic for some times. So ocean alkalinity enhancement. I always have problems saying enhancement. So through the addition of calcium carbonate or like calcium silicate materials, this act to reduce ocean acidification locally. So that draws in CO2 from the atmosphere. It can be achieved like electrochemically, so splitting surface seawater into acid and base, and then pumping like the weekly acidic waste stream below 2,000 meters depth, and then leaving the more like the alkaline waste stream to be put back into surface waters to increase like alkalinity and pH. There are different ways of doing this. These include like spreading finely ground alkaline substances over the open ocean, depositing alkaline sand or gravel on beaches or coastal flats, and then the reacting seawater with alkaline minerals inside the reactors before releasing the modified seawater back into the ocean. So this technique may counter ocean like acidification, and increasing ocean pH via alkalinity enhancement may then be directly beneficial for like organisms that are vulnerable to like ocean acidification. I'm sure we all heard about photosynthesis. So importance of macroalgae, like macroalgae farming could contribute to carbon removal in 3 major ways. First is like some farmed or like wild macroalgal like detaches from like the main farm line and sinks to the seabed, and taking the like with them the sequestered carbon. Second, we have like harvested macroalgae could like be used to create like biochar or like other like long-lived products like bioplastics. And then third, the macroalgal biomass could be harvested, like compressed, and then sunk into the deep ocean for like permanent like carbon sequestration. As we have the whole ocean available for this, the potential production is immense. However, the actual like CO2 sequestration potential is still like a little bit under debate. And when looking closer, the consequences for like all like our oceans can be quite severe, but we can have a better look together. Oh yeah, and by the way, if you're really interested in this topic, this paper by Lisa Levin, it's really great, and you can follow also like Lisa Levin. She's done a lot of research regarding like MCDR and deep sea. So some considerations here. So this paper includes other approaches as well, which is like such as like ocean thermal energy conversion, like OTEC, which uses like thermal differences between surface and deep waters to produce energy. Then we have like also carbon capture and storage as liquid CO2 injections, and then we have like coastal blue carbon and crop waste deposition. So what are the impacts? We talked about ocean alkalinity enhancement, so which involve like fine like or inorganic particles, or for example, artificial upwelling can like alter like ocean reflectivity and turbidity, and this can impact like life field and heat distribution as well. So in the instance of like OTEC, the like cooling methods change like heat distribution, and these can affect like mid-water processes like vertical migration, oxygenations, like particle flux to the deep sea, and this can like lead to like cascading effects to seabed ecosystems as well. Changes in like plankton productivity and distribution affect like marine food webs, nutrient supply, ecosystem connectivity, and the smaller particles may be transported as marine snow to the deep sea, and as the influx of like increased like particular organic carbon or POC may significantly alter deep sea sediments processes. Large-scale macroalgae cultivation may increase like nutrients limitations, such as like nitrogen or like phosphorus, and this can affect like open ocean phytoplankton composition and productivity. Organic matter release from macroalgae or crop waste during the descent can alter microbial production, oxygen consumption, like food supply in deeper waters, impacting like food webs and biodiversity as well. But also this increased like organic matter reaching the seabed can disturb like the biota in the sediments and might deplete oxygen and then attract like opportunistic species, affecting like species interactions, composition, like reducing biodiversity, and can lead like to harmful conditions like anoxia. So and also macroalgae like rafts could act as vectors, like spreading coastal contaminants, parasites, and other invasive species into the open ocean and into the deep waters. And all of these interventions could like undermine critical deep sea ecosystem services like carbon, cycling, and fisheries, for example. And this leaves us with the following, like we could have indirect effect on carbon flux burial. And so like ecosystem function needs to be considered in the assessment of large-scale ocean interventions. So, as we all know, oceans are quite well connected. So the interconnectivity of the ocean like presents challenges in establishing like decision-making processes and regulatory standards for these activities, which currently fall like under various national and international treaties, such as like UNCLOS or like the London Convention or like the London Protocols. And we have to consider that we have like organic versus like inorganic inputs, and then these are like treated like differently within like national or international jurisdictions. So these elements might all be regulated differently, and the amendments to these protocols and treaties would require like a really detailed environmental assessments for the use. There are like sometimes there are like unclear and insufficient regulations regarding these techniques. Like, for example, like seaweed culture or like sinking, and the development of like integrated governance framework, like the BBNJ treaty is essential, which must consider like and respect direct and secondary effects with other deep sea activities. So these approaches are not the only thing that's impacting the oceans, and also in relationship within like existing treaties as well. So what is the future? While like marine CDR technologies are in the early stages of the development, there is an urgent need to assess their like effectiveness and potential risks to deep sea ecosystems. So we have to consider like trade-offs between mitigating like climate change and the negative impacts on marine biodiversity must be like transparently like evaluated. And global cooperation is crucial to ensure like marine CDR activities align with ocean conservation goals. Integrated governance and data sharing mechanisms, such as like the BBNJ agreement, and collaborations like among ocean governance institutions are like needed to support transparent research and policy development for MCDR, so we do no significant harm to the marine environment. So we said that it's still at early stages and requiring like accelerated interdisciplinary studies to better understand the risks, benefits, and the scalability of these technologies. We have to consider like environmental and social impact assessments are like necessary to ensure these activities don't do any harm to deep sea ecosystems and communities. We have to balance like control lab research with large-scale field studies, so we can understand like real world impacts of these technologies. And there's like a holistic approach also is needed to address the potential ripple effects across the regions and between different technologies. We should involve like local community and traditional knowledge holders is essential for ethical, transparent marine CDR development that aligns with local needs and also like the more global conservation goals. So last but not least, there was a funding call, and the deadline was the 16th of October. I've submitted a pre-proposal, so if anyone is interested in collaborating, please let me know. The funding call is for developing an environmental impact assessment framework for marine CDR. Hopefully we'll be selected to submit like a full proposal, and thank you very much for your attention. Oh yeah, I'm gonna be changing jobs, so I won't be at HarryWatt anymore. But if you wanna collaborate on something else, please reach out anyway. Okay, bye. Thank you.